Right. Now, who's ready to work some problems? All right, so first thing that I'm going to do is I am going to find my pK values. And I'm going to do that by taking a negative log of my Ka1 and Ka2 to find my pK1 and pK2. So I'm going to pause it while I do this so this video is not like 10 years long. Right, so I've got my pK values now. So what we're going to do is we're going to solve for the pH of the solution containing 0.049 molar of NaHZ. And remember, this is the one, I'm sorry, I have to turn this weird. I'm going to turn the camera so that you guys can actually still read. We're going to do pH equals 1/2 of pK1 plus pK2. And if you guys can hear my kids in the background, I'm not sure if you can, they are playing Lego Harry Potter and loving it, but they're very loud, so sorry. Okay, so I've got my pK1 plus my pK2, and then I'm going to add those together and divide it by 2. So I'm going to pause that and do that real quick. All right, and that's going to give us a pH of 6.40. Right, now let's move on. So here we've got the pH of a solution containing 0.049 molar of Na2Z. And as we discussed before, this is one where we're going to find the Kb value here, and then we're going to set our Kb, and because we've got Ka2, we're going to do Kb1, and that's going to equal our, hold on. All right, so the easiest way for me to do these is I'm going to write out the reaction. And then that way you can tell exactly what you're putting up there. So remember, our Na is just kind of a spectator, but this becomes Z2 minus, okay? And that's going to react with our water. So we're going to have Hz minus plus OH negative. All right, and these are what we're going to put over here. And then we put this over the concentration of our Z2 minus, right? So first things first, let's solve for Kb1. So Kb1 is going to equal Kw divided by Ka2. And I'm going to run those numbers real quick and pause the video so it's not terribly long. All right, and just as a reminder, Kw is 1 times 10 to the negative 14. And then we're going to divide Ka2 out of that. And that's going to give us a Kb1 of 1.887 times 10 to the negative 6. So when we set this into our Kb equation, we're going to remember that Hz minus and OH negative are going to be the same value because this is equilibrium. So this is going to equal x squared over our Z2 minus value. And then if we solve that for x, and how we're going to solve that for x is we've got to multiply both sides by the Z2 minus and then square root it. So our x is going to equal the square root of Kb1 times the concentration of our Z2 minus. Now we're going to sub in some values. And our Kb1 is 1.887 times 10 to the negative 6, and we're going to multiply that by 0.049. And that is going to give us an x value. I'm going to pause this and run those numbers. Hold on. All right, that's going to give us an x value of 3.04 times 10 to the negative 4. Now remember that this is not our pH. This is our concentration of our hydroxide. Okay, and so from this, we're going to find our POH. And that's going to be our negative log of 3.04 times 10 to the negative 4 is going to give us our POH. I'm running out of room. So our pH is going to be 3.517. And we're going to subtract that from 14 to give us our pH. And that is going to be equal to 10.5. There, for our pH on this one. And again, sometimes these problems do take a lot of space, but I am writing pretty big, and there's a lot of extra stuff. All right, so part C, pH of a solution containing 0.049 molar of H2Z. And again, this is our K1. Here is our equation. So we're going to write out, this is going to be equal to x squared over H2Z, right? And then we're going to solve this for x. So x is going to equal square root of Ka1 times the concentration of H2Z, and x, which is also equal to the hydrogen ion concentration. So let's remember that one when the time comes. So Ka1, it gives us as 3.1 times 10 to the negative 5 times 0.049. And that is going to give us an x of 0.00123. And that is equal to our hydrogen ion concentration. So if we take and plug that into our pH formula, all right, so that's going to give us our pH is going to equal 2.91 on this one. All right, we are getting so close, guys. All right, so again, we are down here, and these are the Henderson-Hasselbalch ones. So we've got the pH of a solution, and it gives us our two concentrations. So we just have to remember which pK value to use. And if you can look at how these are going to dissociate, remember your sodium is a spectator, so you just have to kind of pretend like that's not there. And then he shows which one to look at and add in there on here, okay? So we're going to do pH is equal to pK2 plus the log of, and we've got Z2 minus, which is right here. So that's 0.063 over 0.082. And then we're going to plug in our pK2 number, which we're going to come up here to where we figured that out. That is 8.28. And then we're going to get a pH equal to 8.17. That looked like a number sign. All right, last one. And again, this is another Henderson-Hasselbalch one, okay? But we're going to plug in pK1. So our pH is going to be pK1, which is 4.51 plus the log of, and we're going to do our HZ minus over our Z. So again, we're pretending that the sodium doesn't exist because it's just kind of there, right? So our sodium one is going to go on the top. That is 0.076 over 0.092, and that is going to give us a pH equal to 4.43. Once you know what equations to pick in here, it really does make it a lot easier to be able to decide what you're going to do, what you need to do. If you guys have any questions, drop in the comments, text, or email, and good luck. I'll talk to you later.